Section 2.4 is about rates of change and tangent lines. We've talked about, whether we've called it this or not, we've talked about average rates of change for years. An average rate of change is written with a delta symbol, and most of the time we talk about our delta y over delta x, like the slope of a line. When you have a line and you find its slope, you do rise over run, its change in y over its change in x. So an average rate of change is a slope. So for example, if we have a function 2x squared plus 5, and we want to find the average rate of change from x equals 1 to x equals 3, then all we need to do is find the delta y, so f at 3 minus f at 1, over the delta x, 3 minus 1. Well, f at 3, we plug this in, 3 squared is 9, times 2 is 18, plus 5 is 23, minus, and then f at 1 is 7, over 3 minus 1 is 2, so we get 16 over 2, or 8. So this is the average rate of change from 1 to 3 along this function. Well, what does this function look like? It's a parabola. We know that because it's a quadratic, a degree 2 polynomial. So if we draw it in here, we know that it looks something like this. Now, what we have when we're looking at the average rate of change, if we have x is 1, we're right here. And then for x is 3, we're right here. Now what we found was the slope of this line connecting these 2 points. So this is the slope of this line here, this blue line. And that tells us the average rate of change along the function from 1 to 3. When you're looking for average rate of change, you use these lines and find their slopes to help you. And this line is called a secant line. A secant line is any line along the function where you take 2 points on the function and connect the dots. It gives you average rate of change. Now, sometimes we're looking for the average rate of change along really small intervals. Let's say we have a function that looks something like this. And we've got this x value here. That's one of our points we want to look at. And let's say we've got this other x value here, and we want the average rate of change between these two. So we would draw a secant line, and here we'd find the slope of that secant line, and then we would have our average rate of change. So what happens if we get closer though? Let's say we get closer in here, and we draw our secant line in, like so, and then we get even closer in here, and again we draw our secant line in, now what you notice is that the line is getting closer and closer to this x naught, this space between the two, the delta x, is getting closer and closer to 0. When we finally get to the point where it's all the way up to the x naught, we have what's called a tangent line. So if we have no delta x at all, we have a tangent line. And what a tangent line is it hits the function right at that one place and nowhere else. It only touches it right at that one place. And the tangent line gives us an instantaneous rate of change. So this secant line gives us the average rate of change. The slope of it is the average rate of change from 2 points on the function. And the slope of the tangent line gives us an instantaneous rate of change. So what does that mean algebraically? How can we figure that out algebraically? Well, for average rate of change, we've got f at our x naught plus delta x, that space between them two, minus f at our x naught. So if we have our function here, so we've got x naught, and then we've got this next space here where we're delta x away. And we're looking at these 2 points, and what we're saying is the y value here, x naught plus delta x, minus the y value here, the x naught, minus, and then on the bottom is the x naught minus delta x, or plus, sorry, minus x naught. So this is our average rate of change. It's the slope of that secant line that we just looked at. Now what happens with our tangent? With our tangent line for instantaneous rate of change, what we're looking for is what happens when this delta x is going towards 0. Well, if you simplify this out, you see that these x naughts are going to cancel, and you're going to be left with just delta x, which means if our delta x is 0, that function is undefined. But we can look at the limit. If we look at the limit as delta x goes to 0, then we will get our instantaneous rate of change, or the slope of the tangent line. Now, we're going to look at some other ways to do this, but this is kind of a foundation of calculus, this slope of the tangent line using this limit here. So, this is our slope of our secant line, the average rate of change, and this is our slope of our tangent line, the instantaneous rate of change. There's only one tangent line at every point on a curve, so that slope of that one line is what's going to tell us about the rate of change. Make sure you understand how we get from average rate of change to instantaneous rate of change, what it means to have the change in y and the change in x, and how we use this limit to get us an instantaneous rate of change. All right, let's try some examples. So, find the slope of the tangent to y equals 3x minus 6 at 1, negative 3. Now, you may be saying to yourself, it's a line. If it's tangent to it, then it is the same line. Obviously, the slope is 3. That's true, but let's look at how it applies with the calculus so that we can make sure we've got this concept under. All right, so we know that our x naught is 1. This is our x value that we're at. So if our x naught is 1, the slope of the tangent line is the limit as delta x goes to 0 of f at our x naught plus the delta x minus f at 1 over the delta x. So we simply use our algebra, plug this in, so we have 3 times 1 plus delta x minus 6 minus 3 times 1 minus 6 all over delta x. So now we need to simplify this down. The limit as delta x goes to 0 of 3 plus 3 delta x minus 6 minus 3 plus 6. All right, all over delta x. Well, it simplifies very nicely. and you have 3 delta x over delta x, which means those cancel, so we just get 3, which is what we knew was going to happen, but you can see how we use this definition of the slope of a tangent line to be able to calculate out slopes. Now let's try one that's a little bit more complicated maybe. So find the slope of the tangent. To y equals x cubed at the point 0, 0. So this means our x naught is 0 because that's our x value we're looking at. So again, we take the limit as delta x goes to 0 of f at our x naught plus that delta x minus f at our x naught all over delta x, because this is the definition for the slope of the tangent line. So we simplify this out. So we've got 0 plus delta x cubed minus 0 all over delta x. I guess I should write that in there. So 0 plus delta x is just delta x. So we have delta x cubed, and then minus 0 cubed is just 0. So that's delta x. So that simplifies even further. And we see that our limit is 0. Now what that means is when we have our x cubed function, if we put a tangent line in right here, it would be right along this axis because it would have a slope of 0, which means it's a horizontal line. Now, we've talked about secant lines and how that's 2 points on a curve, and then we talked about tangent lines. It's just one. There's one more that we need to talk about, and that's a normal line. A normal to a curve is perpendicular to the tangent. So if we have a function, say it just goes like this, and we have a tangent line, let's say right here, our tangent at this point here, then our normal would be right here because it's perpendicular to that tangent line. So in example 1, the first one we did where we had a slope of 3, the normal would have a slope of negative 1/3 because remember the perpendicular, if we have a slope of 3, then the perpendicular slope is opposite reciprocal. So we're going to have to find secant lines, tangent lines, normal lines. You've got to make sure that you remember how to do that. You also need to make sure you remember how to find the equation for lines because we'll be asking for the equation of the normal line or the equation of the tangent line. Once you've found the slope, at that point we know which point it goes through. Now, we've talked about that a lot of the things that we do in calculus is applicable to physics, and so we're going to do a little bit of an example with that. One thing that you need to realize is the position function for a falling object is 16t squared. That has to do with the gravity, gravity constant, 32 feet per second squared. So this would be in feet. And the way we derive this formula, we're not going to deal with right now. But if this is the position function for it, and we want to know its speed, then its average speed, remember that's the delta y over the delta x, then we're going to have, in this case it would be delta y over delta t, depending on the time. So whatever time value you're looking at, the start time minus the finish time. Now, often we will use, instead of delta x, we'll use an h, especially when we're dealing with these time things. So the way we could write this is, if this was f at t, then we would write f at t plus h minus f at t over, and then again, of course, it'd be t plus h minus t, which is just h. So it's the same exact formula, we just changed the letters a little bit because we were talking about physics stuff. So this is going to this gives you your average speed. If you have this position function here, this will give you your average speed. And your instantaneous speed, of course, would be the limit as h goes to 0. So if we plugged this in, we would have 16 times t plus h squared minus 16 t squared all over h. And we can FOIL this out. We get t squared plus 2ht plus h squared. And then multiply it by 16. So we have 16t squared plus 32ht plus 16h squared minus 16t squared all over h. So these cancel. And we just keep simplifying. We have h times 32t plus 16h all over h. So those cancel, and we're left with 32t plus 16h. This is our average speed. This is the interval over which we're looking for the average, and this is the initial time. So if we want our instantaneous speed, we would take the limit as h goes to 0 of 32t plus 16h, because remember, basically the tangent line, all you're doing is you're taking the slope of the secant and taking the limit as that space between the 2 points goes to 0. So we took our secant slope and we simplified it down to this. So for our tangent, or our instantaneous speed, we would have this, which would give us 32t. So this is our instantaneous speed. Instantaneous speed. Now, of course, there's all kinds of physics things that will make this an exception to the rule. These are only formulas that work out if you start out from a standstill and you're starting at point 0 and those kind of things. But you see the way we get this, the way we derive this from the position to the instantaneous speed. So this is our average speed, and this is our instantaneous. By using this definition here, we've got the slope of the secant line, and then here the slope of the tangent, which is just the slope of the secant, take the limit of the space between them that goes to 0. So hopefully we're clear on the difference between a secant and a tangent. We know what a normal line is, and we can deal with the tangent line and finding its slope so that we have an instantaneous rate of change, an instantaneous speed, for example, which is a kind of rate of change of position. And we know how to deal with this. It is essential. This is like a key building block in calculus. It's essential that you understand the relationship between the slope of the secant line and the slope of the tangent line and how you go between the two. So make sure you've read the section. Go over this video again if you need to. Make sure you've got some good notes and have looked at this, and then we'll go over it some more in class.